Hi! Today we'd like to show you how we can bring together some very simple models to create a unified theory to describe pump-probe experiments. We're only going to need two tools, the Born-Oppenheimer approximation
and time-dependent perturbation theory.
Let's set the stage for the players in this game. Chapter 1. To boldly go where no Born-Oppenheimer has approximated before. We start our journey at the familiar molecular Hamiltonian. There's kinetic and potential energy terms for both the nuclei and the electrons, and to make matters even worse, we have to consider their potential interactions with each other. Most of the time, this is impossible to solve, so alas, we are forced to tackle a lesser portion, the electronic Hamiltonian. Solving for the eigenvalues and eigenfunctions of this Hamiltonian is like fixing the nuclei in space and looking at how the electrons fly about this clamped nuclear framework. We could feasibly solve this equation for every possible arrangement of the clamped framework and look at how the eigenvalues change for every possible internuclear distance. By connecting the dots, potential energy curves emerge. Now we have the electronic eigenfunctions. Let's make a guess for an eigenfunction solution to the full Hamiltonian. Our electronic Hamiltonian gave us information about the electrons, so it seems reasonable to me that we're going to need some function that looks at how the nuclei behave. Who knows how this is going to work out, but let's be brave and put it in anyway. Here's the result. The second derivative chain rule acting on the electronic eigenfunctions has made some ugly terms pop out. Thankfully, the derivative of the electronic wave function is proportional to its momenta, which is proportional to the mass of the electrons, and since we're dividing these terms by the mass of the nuclei, quite often we can ignore these last two terms. This is precisely the Born-Oppenheimer approximation. Tidying everything up, we get this. This is the time-independent Schrödinger equation for nuclear wave packets moving under an adiabatic Hamiltonian. What's important to see here is that the nuclei are going to interact with each other, and the averaged electron-electron and electron-nuclear repulsions contained in the potential energy curves. In general, wave packets are going to move along these potential energy curves, depending on the shape of the line. The potential energy curve could be unbound, in which case the wave packets will slide out and the molecule will dissociate. Or they can be bound, in which case the wave packet may bounce around the well. In the bound case, there will be vibrational energy levels within the curve, just like the simple harmonic oscillator. So that's how we're going to approximate our molecule. But using the Born-Oppenheimer approximation means nothing exciting is going to happen unless we're the ones who cause population in one level to move to another. To make this happen, we can use light, and for a theoretical description of this, we turn to perturbation theory.
Chapter 2. Time-dependent perturbation theory. Exciting stuff. Perturbation theory allows us to take a Hamiltonian that we would normally struggle to solve and approximate it by a known Hamiltonian plus a little extra interaction. The effect of this term must be small compared to the known Hamiltonian for the approximation to be valid. Let us consider our time-dependent wave function. We might guess that the wave function solution of the full Hamiltonian is going to resemble that of the unperturbed system, plus some small higher order terms due to the perturbation. These lambda in our power series are used so that we don't lose track of our different order terms in our expansion. Let's substitute into the full time-dependent Schrödinger equation with our guess and match terms that have equal powers in lambda. Wow! Reassuringly, the time-dependent Schrödinger equation for the unperturbed Hamiltonian falls straight out of this. Now we have to just solve a set of differential equations. I'll spoil it for you. These are the solutions. These are different order correction terms for our expanded wave function, with our order parameter lambda now set to 1. We might notice that the first and second order terms look very similar. The only difference is that the first order term takes the 0th order term as its input, whereas the second order term takes the first order term as its input. Practically, we don't need to care about the second or higher order terms because we can just apply the logic of the first order term repeatedly. If we were to assume that at some starting time t0 that the Hamiltonian was in the unperturbed state, then the correction terms at this time will be 0, and we can simplify the expression. We can apply this result to any weak perturbation, but it becomes simple when we are talking about very short interactions, which have a clear start time, and so we are free to say that the perturbation starts at t equals 0. This is why having an ultra-short pulse is beneficial, because if we were working with a continuous wave, we would need to specify the start time of the pulse as -infinity.
Chapter 3. Pump-probe experiments made easy. Now we just need to combine the results from the Born-Oppenheimer approximation and time-dependent perturbation theory. When we expose our molecule to light, we can write the Hamiltonian of the system as a sum of the bare molecular Hamiltonian and an interaction with an electric field. From now on, let's consider the simple case of just two bound potential energy curves or states as generated by the Born-Oppenheimer approximation. Because both A and B are bound, we will also need to think about which of the harmonic oscillator-like levels the wave function is in. But for now, let's not worry too much about that. In the basis of these two states, the molecular Hamiltonian may be written diagonally, and the perturbation is constructed from off-diagonal elements. Of course, the matrix to describe the perturbation is non-diagonal in this basis, because we are interested in how the perturbation is going to cause coupling between the two Born-Oppenheimer states. We are using the dipole approximation to model this interaction. Now let's assume that at t equals 0 the system is unperturbed and starts off entirely in the ground electronic state. Let's pull out the expression for the first order correction in the presence of the perturbation that we derived earlier. We've already defined every term in here, so let's substitute in and simplify. What this tells us is that to first order, the perturbation is going to cause an increase of population onto the excited state. This vector notation is no longer necessary, and we can just assume that this first order correction term implies the transfer of population to the excited state. This equation tells a clear story when read from right to left. Starting at time equals 0, the wave function is in the ground state. Whilst in this state, it will be acted upon by the ground state potential. We can simplify the situation further if this wave function is in the ith vibrational eigenstate of this level. If this is true, then it will just acquire a phase as described by the time-dependent Schrödinger equation. Making this simplification, we can replace the ground state Hamiltonian with an energy eigenvalue. At the end of some time t prime, it will be hit by the perturbation, the pulse of light. After this interaction, some amount of the population will be transferred to the excited level. Once excited, it will be acted upon by the potential described by the excited state. We haven't yet specified the shape of our electric field, so let's be explicit about it now. So far, we've been assuming that these pulses are going to be very short. So let's approximate our electric field with a delta function, incident at time equals t1. Fortunately, nowadays, lasers can generate femtosecond pulses, and so it's not so heinous for us to describe an ultra-short laser pulse as a delta function. Let's evaluate this integral using the sifting property of the delta function. We will gain a greater insight into the processes happening if we move all of our constants to the left of the expression. We see that it is these last two terms grouped together that are acted upon by the excited state potential energy curve, and so let's define them as a new effective wave function. It is found that this dipole integral only weakly depends on x, and so it can be thought of as just some constant number. Let's replace it with whatever the result would be in the equilibrium geometry. Thus, the wave function that gets transported to the excited level is an exact replica of the initial wave function, just multiplied or rescaled by some constant dipole value. This is precisely the Franck-Condon approximation, and the region where the excited state wave function is born is called the Franck-Condon region. Our pumped wave function, in all likelihood, will not be an eigenfunction of the excited electronic state, and therefore, technically, we should call it a coherent wave packet that moves along the excited state potential energy curve as we described previously. So that was the simplest case, because there was only one instance of a wave packet being excited. But what if our excitation had some finite width? We can get an idea of what might happen in this case because you can build any function out of an envelope of delta functions. By integrating over this electric field, we see that population is excited at different moments during the pulse. All these excited infinitesimal wave packets will accumulate in the excited state where they will interfere in some complex way depending on the nature of the incident electric field. Let's consider the simplest situation where we will see this interference, an electric field made of two delta functions. A pump pulse hits the molecule at time t1, and a probe pulse will hit the molecule at time t2. The two wave packets excited by these pulses are going to exhibit interference depending on the phase information of the pulses. Any pulse made by a laser is going to have a carrier frequency. It's a little weird to think about how a delta function has a carrier frequency, but in reality these delta functions are just the limits of some Gaussian pulse. Furthermore, the second pulse can have a different phase from the first pulse. Let's assume that our initial wave function starts from the ground vibrational state of the bottom level. Using the same first-order equation from perturbation theory and substituting in our two delta function form of the electric field, we obtain this. Let's factorize this equation into a nice form. Here we have defined a new term. When read from right to left, we see that this new term is the excited amplitude from the first pulse evolving on the excited potential energy curve. Here are the two Born-Oppenheimer states with their vibrational energy levels shown. Life will become a lot simpler if we can define some new variables that reference all energies to the 0-point energy of the excited electronic state. We already said that our initial wave function was an eigenstate of the lowest vibrational level of the ground electronic state, and so we can ignore all higher vibrational levels. Of course, all energies are related linearly to frequency through the Planck relation. We can define a new energy, which is the distance between the minima of the ground and 0-point energy of the excited electronic states. The carrier frequency of the pulse can take us to any energy higher than the 0-point energy of the excited state. We can define a new carrier frequency as how much higher the carrier frequency takes the pumped packet above the 0-point energy of the excited level. We can also define a new excited state Hamiltonian that is shifted relative to the 0-point energy of the excited state. The pump-probe delay can also be expressed as tau. Writing the interference effect in terms of these four expressions simplifies the equation. Now we can make more progress if the excited state behaves exactly like a harmonic oscillator. In this case, any excited wave packet will oscillate in the excited potential with a frequency and period. After one period, the returning wave packet will look the same as when it started. Another benefit of using a harmonic approximation is that the energy spacing between vibrational levels will be constant. Therefore, we will always be able to express the carrier frequency as an integer of the spacing between levels plus a little bit extra delta above the previous level. When delta is not an integer of the spacing, we say that there is detuning. After using these simplifications, we get this simpler expression. Here we can see how the detuning, pump-probe time delay, and phase difference are all going to contribute to the interference between the two wave packets. Let's look at the terms in the brackets, since they will determine the interference between the pump and probe wave packets.
Let's first consider just changing the phase in a situation where there is no detuning. For zero phase difference, the prefactor to the amplitude becomes 2, and the population in the excited state quadruples. There has been constructive interference between the first and second wave packets. If the phase difference between the pulses is pi, then the population becomes 0. This corresponds to deconstructive interference between the pump and the probe wave packets. If there is a pi/2 phase difference between the pump and the probe, then the prefactor would be complex, but the population would double. This corresponds to a situation where the two wave packets overlap, but no interference happens between them. Now let's investigate the relationship between the detuning and the pump probe time delay with the phase difference held at 0. If we make our time delay the same as the period of oscillation of the excited potential and have 0 detuning, we see that the amplitude is going to double and therefore the population is going to quadruple. The first wave packet oscillates once during the time delay and constructively interferes with the second on returning. Equivalently, 0 detuning means delta is just an integer of the level spacing. Therefore, as long as the product of the detuning and the time delay is an integer number of 2π, we have constructive interference. Let's see what happens when we introduce some detuning with the same pump-probe delay. Now our carrier frequency has overshot a vibrational energy level by half of the spacing. In this case, the product of detuning and time delay is π, which corresponds to 0 amplitude and population in the excited state. Our pump and probe wave packets deconstructively interfere upon the return of the first wave packet. Now, if we keep the same detuning, but make the time delay half the period of the oscillation, then the second wave packet is pumped up when the first is on the other side of the potential. Again, the amplitudes change by a complex quantity, but the population doubles. This makes sense, since the two wave packets are too far apart to overlap and interfere when the second is excited. What we have seen is that detuning, time delay, and phase difference all affect the interference we see in the excited state. Often in pump-probe experiments, we choose to have 0 detuning and then vary the time delay and phase difference between the pump and probe pulses. From an experimental point of view, the population in the excited state is expected to be proportional to the fluorescence coming out of the sample as it relaxes to the ground state. From what we have learnt so far, if we can perform a fluorescence pump-probe measurement on a molecule using no phase difference and detuning, and a varied time delay, we would see constructive interference and the largest signals at multiples of the vibrational period. Using a pi phase shift, we would see lowered fluorescence at multiples of the vibrational period, because this is when deconstructive interference occurs most effectively. This experiment would immediately tell us the period of vibration in the excited state.
There's lots of types of pump-probe experiments that we haven't been able to cover here, but the basic theory we've given underpins most of them, and we hope that they seem a little bit less mysterious to you now. The ways we can probe chemistry using this technique are endless, unlike this video.